So for number one, we have three boxes stacked on top of each other. We are trying to rank the magnitude of the forces from largest to smallest. So we have a lot of different options. We have the force of 3 on 2 and the force of 2 on 3. So I'm going to call this F32 and F23. No matter what the circumstance, the force of 3 on 2 and 2 on 3 has to be equal, because Newton's third law says that every action has an equal opposite reaction, and that is two forces acting on each other. So the force of 3 on 2 will be equal to 2 on 3, just in the opposite direction. So those two have to be equal. The force of 3 on 1 and 1 on 3, again, no matter what the situation, those have to be equal. 2 on 1 and 1 on 2, these two have to be equal, and then 1 on the floor and the floor on 1, again, have to be equal. Now, in order to rank them from largest to smallest, it's going to be a lot easier once I've drawn my free body diagram, so I'm actually going to do this part first. So the easiest one to start with is the 3 kilogram box, because the only forces on the 3 kilogram box are the force of gravity and the force of box 2 holding it up. And it says that it is at rest. Yeah, it's at rest, so I know my forces are going to be balanced. So I can find the force of gravity for just this box would be 3 times 10, so 30. And that means that the force of 2 on 3, the force of box 2 holding the 3 kilogram up, has to be 30, because again, they are balanced. Now go to box 2. The 2 kilogram. Of course, it has its own weight, which would be 20 kilograms. And it feels the force of box 3 on it. So box 3 is pushing down on box 2. So I'm going to call that the force of 2 on 3, and that is again 30 newtons, because we said that between two objects, the force between them has to be the same. And then it has the 1 kilogram box holding it up, so that would be 1 on 3, and because it has to be balanced, 20 and 30 down, it must have 15 newtons up. And then lastly is the 1 kilogram. So the 1 kilogram has its own weight, that would be 10 newtons. And the 1 kilogram directly feels a force of 2 on 1. So the force of 2 on 1, oh, I said 3 right here, and that's definitely 1 on 2, not 3. My bad. That should have been 1 on 2, not 1 on 3, because 1 and 3 aren't touching. So the force of 2 on 1 is the same as 1 on 2, so that would be 50 newtons. And then the force of the floor on 1, which is just our normal force, but because up here it called it the floor on 1, I'm going to call it floor on 1. That's floor on 1. Again, has to be balanced, so that would be 60. Now, it also helps to stop and just think through, okay, if this is a total weight of 60 newtons, of course the floor is pushing back 60 newtons, that makes sense. If you look just at the 2 kilogram, so it has its own weight of 20 plus the weight of the 3 kilogram box, 30. So box 1 is pushing up 50 because it's holding up both of those, whereas this one only has a force pointing up of 30 because it's only holding up its own weight, whereas this one's holding up all these two, and then the floor is holding up all 3 of them. So this is at least reasonable, and now we want to go through and we want to make and rank the magnitude of the forces. So the floor on 1 and the floor on, or 1 on the floor would be 60 newtons. 1 on 2 and 2 on 1, so we said that would be 50 newtons here. 1 on 3 and 3 on 1 actually does not exist. 3 is not physically touching 1, so 3 does not exert a force on 1, and vice versa, so doesn't exist. Or you could just say that's 0 newtons, because it isn't 1. And then 2 on 3 and 3 on 2, we said was 30 newtons. So the largest force would be the floor on 1 and 1 on the floor, so that would be G and H. Those two are equal. And then the next largest would be the 50 newtons, so that would be E and F. And then the next largest would be A and B, and then the least, or the smallest forces, would be C and D, because it doesn't exist. So 60 would be greatest, then 50, then 30, and then 0. Right, now the next one is assuming that the elevator is now moving up at increasing speed. That means that it is accelerating up. Now rank the magnitude of the forces still from largest to smallest. So again, no matter what the situation, A and B have to be equal. C and D have to be equal. E and F have to be equal. G and H have to be equal. Now, that means that this is not 60 anymore, right? The floor must be pushing up more than it was before. This is not 50 because this is still 50 down, but now it's accelerating up, so this has to be greater, and this has to be greater, and then this has to be greater right here. So the forces up have to be greater, but then each of these pairs still has to be equal, so it's actually going to end up being the same ranking. So it's not the exact same numbers as before, so it's not 60, 50, 40, etc. And because I don't have the acceleration, I can't like plug in. If you really wanted to, you could make up an acceleration and find these actual numbers. But C and D, 1 on 3, still does not exist. Because of Newton's third law, these have to be equal, these have to be equal, and these have to be equal. And then I know that it is greater, this force of the floor on 1 is greater than the total weight. And then this force of 1 on 2 is greater than the total weight. And this force of 2 on 3 is greater than the weight of the 3 kilogram. But they're all adding to the same like acceleration, mass times acceleration, so it's still the same order. Right, 2, give an expression for the acceleration of an object in free fall that experiences a force of air resistance of air. Use G for the acceleration due to gravity. So free body diagram would feel the force of gravity down, obviously. If it is falling down, then air resistance would be opposing that motion. So I'm going to call it F little air, because that's what it told me to call it. And I'm assuming it's still accelerating down. That air resistance would not be equal to the force of gravity because it's asking me to find the acceleration. So then my net force would just be the force of gravity minus F air resistance. And we can find the net force by mass times acceleration. And we can find the force of gravity by mass times G minus F air. And we're trying to get an expression for acceleration, so divide by M. And that would be my answer. Now, on multiple choice, you might see it look a little different. I cannot just cross off the M's because there's an M in this term, but not in this term. What you could do is you could have said mg over m minus m air over m. Here, the M's cancel out, but not in this one, so that's the same as g minus f air over m. That would be the same as this. Either way, you would get it correct for a free response, but you need to know that they are the same for multiple choice. Number 3, a 500 Newton crate is moved across a horizontal surface at a constant speed, so that tells you the forces are balanced, by a 120 Newton applied force at an angle of 40. The normal force is more than the weight, less than the weight, equal to the weight. Well, if we draw a free body diagram, if we were to split this up, make it into a triangle, this would be the opposite side, this would be the adjacent side. So this would be 120 sine of 40 this way. And then 500 newtons is the weight, so my weight would be 500 newtons. So my normal force would just be 500 minus that, which means my normal force would be less than the weight because I have some force holding it up. So C is less than the weight because the net force in the y direction must be 0 because it is in equilibrium for the y direction. If the angle was increased or decreased, what would happen to the normal force and the acceleration? So let's first start with the normal force. Think about if the angle was 0, if it was just on the ground, my normal force would be equal to my weight force. And then as you increase the angle, as it goes up and up, your normal force is just becoming the FG cosine of the angle. So as you get a greater and greater angle, this is getting smaller and smaller. So as the angle increases, the Fn is going to decrease. And then if the angle is decreasing, then the Fn would continue to increase until it was just equal to the weight. What would happen to the acceleration of the block if the angle was increased? So let's think about the acceleration is coming from this FG sine of the angle. If you go back to flat, 0 degrees, you have no acceleration, it's just sitting there. So the more you increase the angle, the more this FG sine of the angle is a bigger and bigger component. So the the acceleration would be increasing. And if I decrease the angle, the acceleration goes back down to 0, so it would be decreasing. You can also just think about like something sitting on a ramp, like the steeper the ramp, the more it falls down. We are choosing all that apply. The sign is just hanging there, which means that the forces are balanced. So they are in equilibrium. The net force in x and y direction would both be 0. A is saying the tension in T3 would be equal to the weight of the sign. So let's think about, if you were to draw your free body diagram at this knot right here, you would have T2 going this way, you would have T1 up here, and T3 down right here. So we know that these would all be equal. If you were to draw the free body diagram of the sign would say, okay, I have some weight, and then I have T3 holding up the sign. So that means if it's just hanging here, the T3 has to be the weight of the sign. So yes, that is true. Tension 1 is greater than tension 2. So let's look at tension 1 and tension 2. We don't have any numbers to work with. What we do have is that this is a higher angle. It is steeper. It is more in the up and down direction than the x direction compared to this one. And we know that their x components of their forces have to be equal. So in this case, T1 cosine of the angle is equal to T2 cosine of angle 2. So if their x components are equal to each other, the x component of the force is equal to each other, and the x, or this angle is a much bigger angle, then this has to be a greater tension force. So T1 has to be greater than T2. Yes, that is correct, because this times cosine of a bigger angle must be equal to a smaller force times cosine of a smaller angle. The x component of T2 is greater than the x component of tension in T1. No, that is not true. They're equal because the x net force is 0. It's balanced. The y component of T2 is equal to the y component of T1. That is definitely not true because T1 is a greater force and it has a greater sine of the angle. So this is definitely holding up more of the vertical component of the weight than this one, which is a smaller force and a smaller y component. So not true. And be virtual. 7. A 2 kilogram object initially at rest. So I have my mass. I have that it's initially at rest, so V naught is 0. Is accelerated vertically by a rope. The object reaches a height of 3 meters in 5 seconds. So that would be my distance, or I'm going to call it my delta x, and time. And I'm looking for the tension in the rope during the acceleration. So draw a free body diagram. 2 kilogram means I have a weight of 20 newtons. And then it's accelerating up, so obviously my tension force is greater than 20 newtons. Now, in order to find the tension force, I would need to know my net force or my acceleration. But good thing is I have V naught, delta x, and t, and I'm looking for acceleration. So I can use that delta x is V naught t plus 1/2 at squared. 0 times 0.5 goes away. This is 1/2 a 0.5 squared equals my delta x, which is 3. So 1/2 of 0.5 squared gives me 0.125a. And then you just divide over. You should be getting your acceleration is 24 meters per second squared. Now, a lot of people are tempted to just go immediately and be oh, weight 20 down, 24 up, that's 64. But this is my acceleration, not my net force. So I need to find my actual net force, which is 2 times 24. And that gives me a net force of 48 newtons up. Now I can say, okay, if I have 20 newtons down, that means I must have 68 newtons up to give me a net force of 48 up. So my answer was 68 newtons up. Assume that they all have equal mass, so they're holding the same mass, and the strings holding them up are identical. In which case would the string be most likely to break? So let's think about, for A, the tension in the string would just be equal to the weight. So in this one, the tension would have to be more than the weight because it is pulling up the weight, but it's also pulling to the side, to the left and the right, so that's kind of wasting its tension, pulling against each other. Same in this case, same in this case. So I know A is definitely at the answer. That's the least tension, so the least likely to break. The question is here, which one has the most tension in it? So if we think about, they all have to have the same Y component up because it's holding up the same weight. The net force for everybody is going to be 0 because it says it's just hanging there. They're holding them in place. And because you have this weight force down, that means that each of these have the same weight force up from their tensions. So the answer is B, because if this has the same force up as the other ones, that means it must be held super, super tight, super, super taut, and that this tension must be huge, because if you were to draw like your picture, right, say this is your angle, this is your tension sine of the angle right here, and this is tension cosine of the angle, it's wasting so much of its tension pulling this one to the right and this one to the left, that it's only a small part of its tension is actually pulling it up. So it must have a huge tension because they all still have the same weight force up to hold it. Right, number 9, so mass M is pushed at a constant speed up a ramp at an angle theta above the horizontal. So this is the angle of the ramp. And then between the mass and the ramp, there's a coefficient of friction mu. A force F acts on the angled theta, not theta, sorry, this is phi, relative to the surface. So this, it wasn't super clear, that's this angle right here. So I have two angles. I have the angle of the ramp, and I have the angle of this applied force. One is relative to the ground, and one is relative to the surface of the ramp. And we are looking for the force of friction. So first things first, we draw a free body diagram. So I started with my normal force, of course, this way. That's normal. I have Fg cosine of theta, because this is weight pointing down. This would be the theta. Think of like my contraption. Fg cosine is always opposite of the normal for an inclined ramp if I have the angle right here at the ground. And then I would have Fg sine of the angle right here. It is being pushed at constant speed up the ramp. So if it's being pushed up the ramp, then friction must be pointing the opposite way, going against motion. So I actually have friction pointing this way. That's the biggest mistake, is you're used to friction pointing this way. That's if it was sliding down, but here there's some force pushing it up, so it's against the motion. And then this force is what needs to be broken down into its angle phi. So think about drawing your triangle like this. This is your phi right here, and then this is your hypotenuse F. So then this would be my opposite side, F sine of phi and F cosine of phi. So F sine of phi is actually pointing down. This is pushing down to the right relative to the box. So this would be to the right is F cosine of phi, and then down on the box is F sine of phi. Now it's asking for the friction force, this FF. So because this is at constant speed, for the x direction, I know my net force is 0 because constant speed is balanced. So that means that the force of friction plus the Fg sine of the angle, theta, equals F cosine of the angle, phi, like this. I'm trying to get FF by itself, so I'm going to subtract this over. So I have F cosine of the phi minus Fg sine of theta equals force of friction. Just subtract it over. And then the only thing left is to replace Fg with mg. And then I get my answer is D. F cosine of phi minus mg sine of theta. So 10, a 6 kilogram block initially at rest is pushed against a wall by a 100 Newton force as shown. The coefficient of kinetic friction is 0.3 and the coefficient of static friction is 0.5. What is true after 1 second? Is it static friction, kinetic, etc.? So basically this is saying, is this force enough to overcome the static? If it is, then it would start moving. It's now kinetic friction. If it's not enough to overcome it, then it's still static. So first things first, we have to draw a free body diagram. So we know that we have the normal coming out of the wall. It's perpendicular. I'm not sure which way the friction is pointing right now. If there was no force, it would be pointing up. But I have a force pushing it upwards, so maybe it's holding it down. Not sure yet. I have the weight force, of course, and I want to break this applied force up into its components so that I can tell which way friction would need to go. So, I call that weight G, that's weird. 6 kilogram block, I have the weight, which would be 60 kilograms. I have the normal force, which I'm not sure about right now, but I have this right here at 60 degrees. So that makes this side the opposite angle, and that is pushing up, so that would be 100 sine of 60, which 100 sine of 60 gives me 86.6. So that would be the F applied would be 86.6 newtons up, and to the right would be 100 sine or cosine of 60. So that would be F applied for the X direction would be 50 newtons. Now it's not accelerating into the wall or out of the wall, so then the normal force has to be 50 newtons. Now, if you look, you see that the applied force is up and the weight force is actually obviously down, but the applied force is greater than the weight force, so that means if there was no friction, it would be moving up. So friction is always going to go against that motion, so my force of friction is going to be pointing down. Now, it starts at rest, so I need to look and see what the force of static friction would be. So static friction would be the 0.5 times the normal force of 50, which gives me 25 newtons. So force of friction would be 25 newtons. If you add this together, this gives me 60 plus 25 would give me 85 newtons, which is just under the applied force. Just less than the applied force. So then if my applied force is a little bit greater than the force of friction, then it's going to start moving up. So it would start moving up, which means kinetic. And if it's moving up, then the kinetic friction would act downwards. So it would be opposite to that. Number 11. Velocity versus time, we want to describe the net force on it. So is it a constant net force, increasing net force, decreasing, or zero, etc.? So here, this one is a velocity versus time graph. So my velocity is changing. I have an acceleration. Because the slope is constant, that means it's a constant acceleration and it's positive. So this would be a constant positive net force. Here, it's again a constant acceleration because it's a straight slope. But now it's decreasing, so that would be like a negative force or going against the motion. So this would be a constant but negative F net. And then here, this is constant velocity, so that is no net force at all because it's constant velocity. So forces would be balanced here. This one would have a greater force opposite to the motion. This would have a greater force with the motion. Elevator problem. So a person is standing on an elevator and their scale would either read somewhere between 0 and the weight, more than the weight, equal to the weight, or 0. When the elevator is moving up, so that would be velocity up, but slowing down, that would mean the acceleration is opposite to the velocity. That would mean acceleration down. So if the elevator is accelerating down, you always have the same weight force. That means that your Fn would be less because I have a greater force down. So if it is accelerating down, that means Fn is less than the weight force. If it accelerates up, then that means that my normal force is a bigger force up than down, so Fn would be greater than Fg. So in this case, it accelerates down, so that would be Fn less than Fg, so between 0 and mg. If it is moving down with decreasing speed, so that's going against the motion, that would be accelerating up. Accelerating up, normal force is greater than the weight, so C. When it is moving up with increasing speed, moving up and getting faster, same direction, again accelerating up, that's situation C, greater than the normal force. When it's moving down with increasing speed, so that's acceleration in the same direction, accelerating down would be normal force less than the weight, A. And then constant speed means they're balanced, so it would be equal to the weight, B and B. Doesn't matter if it's moving up at a constant speed or down, or if it's at rest, it's balanced. 13. A force F pulls on a box of mass M at an angle of phi. When the angle is halved, what happens to the normal force and the acceleration? So I have it at some angle. If it is now a smaller angle than before, that's a weird diagram. So now it's not pulling up as much. So that means that it has a greater normal force. That means the floor must be pushing up more. So I'm going to cross off A and C because I know my normal force increases. And the accelerations, let's think about, see how it's pulling to the side more than it was before, then the acceleration must increase. So normal and acceleration would both increase. Now some of you might say, wait, but if I have a greater normal force, then I have a greater friction force. And that is true, but think about your force of friction, or I think it says little f, is mu Fn. So whatever your mu is, it's always some decimal, times the normal force. This might be a little bit greater, but because it's being multiplied by a decimal, then this is a small change, whereas here, going from one angle to a half that angle, I get a much bigger change in the x direction. So that makes up for this being a little bit bigger, if that makes sense. All right, number 14. So I have two blocks attached. We're talking frictionless, thank goodness. And then the incline creates an angle theta with the floor, which is the type of angle I want when it's relative to the ground. And we want to know the acceleration of them once they are released or run. So acceleration of block 2m is the same acceleration that 3m has because they are physically connected. Free body diagram for 3m is easy. It's 3mg and then the normal force and then just tension because there's no friction. The 2 is a little bit harder because I still have some normal force like this. I've got tension this way, and then I've got weight straight down. This can be broken up. The across from the normal force is always the weight cosine of the angle, and this is Fg sine of the angle, and then tension going opposite to it. So write your net force equation. For the 3m block, it's easy. It's just the tension. So 3ma equals tension. And for, that's a 3m. Yeah, this is 2m. So then net force for this guy, and it's going to accelerate this way because the only force on this one is pulling it to the right, would be Fg sine of the angle minus tension. We can replace F net with 2ma, Fg with 2mg sine of the angle minus tension. Tension is actually 3ma, so let's move this over. 2ma equals 2mg sine of the angle minus tension, which we just said was 3ma. Add that over, that's 5ma equals 2mg sine of the angle. M's cancel, and then divide the 5 over. So 2/5 g times sine of the angle. 2/5 g times sine of the angle is b. And we always check and think through, like, is this reasonable? Yes, it is, because the reason it's being pulled down is the 2m times sine of the angle, and then that's divided over the total mass of 5m. 15. So a force of 50 newtons pulls three blocks of masses 20, 10, and 5 respectively. So this is 20 kilograms, this is 10, and this is 5. Find the tension in A, B, and C, and we're dealing with frictionless. And the force pulling it is 50 newtons. So draw a free body diagram. Obviously we have weight and normal. It would be 200 and 200. But this is balanced up and down, and I don't need the normal for friction, so it doesn't really matter here. And then I have the tension in A pulling it to the right. Now this guy has the tension in B pulling it to the right minus tension in A, and B would have to be greater because it is accelerating this way. And then of course the 100 and the 100. And then lastly, the third box has tension C, and then minus B, and C would have to be greater because it is going to accelerate to the right, and then 50 and 50. So now we're going to write our F net equation. So F net is equal to TA, and that would just be 20 times the acceleration. This one, your F net would be TB minus TA, which would be 10 times the acceleration, is TB minus TA, which was just 20A, so you can add that over, so 30A is equal to TB. And then F net here would be tension C minus TB. F net would be 5A. TC would just be the 50 because this rope is being pulled with 50 newtons. There's nothing else, like, right? It's pulling on this rope, so tension 3 is 50 newtons. And TB was 30A. So add that over, you get 35A is 50. That gives me an acceleration of 1.43. And then now you just go back and replace. 20 times that would give me TA is 28.57. And 30 times the acceleration gives me TB is 42.86. And then we already said that TC would just be the 50 newtons. And it makes sense that TC is greater and then TB and then TA, because TC is technically pulling all of these masses at the same acceleration, that B is pulling just the last two, and that A is pulling just the last one. Right. 16. A 50 kilogram block rests on the horizontal surface. The coefficient of static friction is 0.5. Coefficient of kinetic friction is 0.35. And a force of 260 is applied as shown. So let's look. We have the force of gravity would be 500. The normal force would be 500. And then this applied force of 260. And it was at rest at first, so if it's going to move, you have to have a greater force than static friction. So let's find the force of static friction, what it could be. 0.5 times 250, or sorry, times 500, which gives me 250. So if you look, the most that the static friction could push back is 250. If it's being pushed with an applied force of 260, that is greater than the static friction, so then it starts to move, so it does not remain at rest. So it definitely is going to start moving now. And now, once it's moving, we would use the coefficient of kinetic friction, which would be coefficient, or static, kinetic friction would be 0.35 times the 500, and 0.35 times the 500 gives me 175. So then once it's moving, friction is only going to push back or resist with 170 newtons of force, so then it would accelerate to the right, so you have a greater force to the right. Key there is you need to check and make sure that it is greater than the static friction before it starts to move. 17. A 1,000 kilogram car is initially traveling at 30 meters per second. The driver applies the brakes. The braking force is 9,000 newtons, and if it decelerates to a complete stop, how far does it travel? So I'm looking for the delta x, how far it travels. I have the initial velocity, v naught, I have the mass, I have the force that it brakes with, and it goes to a complete stop, so v is 0 at the end. Now, let's think about if you have the braking force and the mass, that can give me the acceleration, like the deceleration of the brakes, because F equals ma. This technically is like my net force, like the braking force or the average force that brakes it. So that would be 9,000 equals mass of 1,000 A, so my acceleration is 9. Technically it would be negative 9 because it's going against the motion, but we don't really have to worry about that. And then, because I have v naught, v, I have a, and I'm looking for delta x, I'm going to use the v squared equals v naught squared plus 2a delta x. So now I plug in, 0 squared equals 30 squared plus 2, acceleration is 9 delta x. That is, I can just use my calculator, 30 squared over 18, 50, and again, this is going to give you a negative sign. Technically, my acceleration would be negative because it's the opposite direction of the initial velocity. It's going against that. So technically, it would be a positive displacement because it goes forward 50 meters as it deaccelerates. Somebody pushing a lawnmower across a horizontal patch of grass, constant speed means the forces are balanced in the x and the y direction. And we are trying to see which magnitudes would be greater. So if you think about, obviously we have the weight down, that is not going to change, and then the force P is pointing down and to the left, so I feel some P, let's say this is the angle, right here, then this would be P cosine of the angle, and then down would be P sine of the angle. And then we, of course, have the normal force up and friction going against it. And we know that these are equal and these two equal the normal force. So if we look at this, first looking at P and F would not be equal to each other because it's only the x part of P that's equal to F, so P must be greater than F. So we can cross off B and D because P has to be greater than F. And then my normal force would be greater than the weight because it's the weight plus the y component that's being pushed down that equals the normal, so normal would be greater, so A. 10 kilogram box shown is sliding to the right. Horizontal force of 10 newtons is being applied to the right. So it's moving to the right, and then there's also applied force of 10 newtons. The coefficient of kinetic friction is 0.2, so my force of gravity is 100, that means my normal force is 100, and then mu Fn would give me a friction force of 20. So that means that I have a greater friction force than is being pushed, which means that there's going to be an acceleration to the left. And because it is moving to the right and their acceleration is the opposite direction, that means it's going to slow down or decrease in velocity. And the reason I know there's an acceleration to the left is because my net force is to the left. So I have greater force to the left, so that'll accelerate that way. Now that does not mean it is moving that way. It means that the acceleration is that way, which is why it slows down. Okay, ranking the stack of 3 blocks on the table as shown. Which of the following is a valid ranking? So first of all, between any 2 blocks, they have the same force. So like between 2 and 3, like 3 on 2 and 2 on 3 would be the same. 1 on 2 and 2 on 1 would be the same. And the table on 1 and 1 on the table would be the same. So if we look, the ones that are equal, that's table on 1 and 1 on the table. That's true, these 2 would be the same, but it would not be the same as 2 on 1. Because if you look, let's think about, the table is holding up 2m, m, and 3m, so all of this weight. So it's holding up 6 mg on the table, whereas this one is just holding up, so like block 1 is holding up just 3 mg on the table. So B you can cross off because 2 on 1 is not equal to the table on 1. This one says that 1 on 2 would be greater than 2 on 1. That's not true. They have to be equal, Newton's second law. This one, let's see if there's others I can cross off. No, we have to actually look. Well, we already said table on 1 would not be equal to the block 2 on 1. So what's left is C. Let's think about 1 on the table would be equal to the table on 1, which we said is holding up 6 mg of, like, the total weight is pushing back equal to the total weight. And then 2 on 1, so block 2 on 1 would be equal to the 3 mg because it's pushing back all of this weight. And then 3 on 2 would be just holding up this weight, the 2 mg. So this one would be greater than this one, so C is correct. 2 blocks in contact, frictionless surface, 36 newtons is applied to X as shown. It's super light, but it's being pushed to the right at 36 newtons. And we want to exert the force exerted by Y on X. So we're going to draw our free body diagrams. We, of course, have gravity and normal, but it's frictionless and it's accelerating sideways, so those are just going to be balanced. They're not going to affect us. And then this one feels an applied force of 36 newtons. And because there's block Y sitting right here, it's pushing back on it. So I'm going to call this pushing back force the block force. And then the 20 kilogram does not feel the 36 because the 36 is only exerted on this one. What the box Y feels is the force of box X pushing on it. So it's pushing it to the side and then gravity and normal, just like before. It says frictionless, so we don't have to worry about it. So my net force here is 4A, and it's equal to 36 minus the B force. And my net force here, 20A, is just the B force. So now you can go back and plug in 4A equals 36 minus 20A. Add this over, you get 24A is 36, so my acceleration is 1.5. Now, careful, because I didn't ask for acceleration. I want the force of Y on X. So that's the block force, so it's just 20 times the A 1.5, gives me my block force is 30 newtons. Now the trick here is which direction. So let's think about y on x. So y pushes x against the motion, right? Y pushes x this way, x pushes y to the right, but y pushes x the opposite direction, equal but opposite, so it's 30 newtons to the left. Okay, number 2. So this is the one I told you guys to skip in class. This one's kind of a tricky one. We haven't done one exactly like this before, where it's 2 on top of each other and the friction between the 2. So first things first, draw a free body diagram for the 7 kilogram object when pulled with force F. So if we look, obviously we have the weight force, which would be 70 newtons. I've got this applied force F. In addition to the weight, I also feel this force of object, the 2 kilogram object on top. So we can call that the, what did I call it? The force of the box. I called it the force of the box. So the force of box 2 on box 7 would just be the weight of 2, the 20 kilograms. And then, of course, you've got the normal force from the floor. I'm going to call it normal force of the floor because there's kind of another normal force later on. So right now, just the normal force of the floor. It's not accelerating up or down, so that would just be 90 newtons. And then we have friction going against it. So there's friction from the floor. And this is the tricky part, you also have friction from this object right here. So in addition to like the floor slowing it down, we also have the friction of this box. So think about if I have this on top of this guy and this one's being held in place, when I pull this one, these two are also rubbing together. So I have friction between the calculator and the paper and between the calculator and the remote. So there's friction on both sides where it's rubbing materials that would slow it down. So I have friction on the floor and I have friction between the boxes, which I know there's friction between each because it gives me the coefficient of friction between the blocks and between the block and the ground. Now drawing the free body diagram for the 2 kilogram box. So the 2 kilogram feels its own weight, 20 newtons, and then it feels this normal force from the box. So I'm going to call it F box. Technically that is like a normal force. It is this how much the 7 kilogram is pushing up on the 2 kilogram. It's just the normal force from the box, so it's just 20 newtons. Which is what we had before, and also it's not accelerating up or down, so these should be equal. And then it feels tension this way. And then this is the tricky part. The friction of between the boxes is going to point to the left for the 7 kilogram box, and it's going to point to the right for the 2 kilogram box. So force of friction between the boxes. And the reason why is because think about the friction of the calculator on the remote and the remote on the calculator. Those are the same force. They have to be in opposite directions. So if this one points to the left, then this one must point to the right. Also, if you have it sitting right here, this is hard to show. But when I pull it this way, they're going against one another. Okay. I want to know the tension in the string when the 7 kilogram block is pulled with force F. So if you think about it, the tension in the string would only be as much as the force of the box. This force applied only is being pulled this way. What this one feels a force to the right of is just the friction force. So the tension can only be as much as the friction unless you get an additional force in here. So let's find the force of friction for the box. It's going to be mu Fn. The coefficient between the boxes, it says coefficient between the blocks is 0.6. Now we need to think through carefully which normal force we're going to use. So between the boxes, we would not use the normal force from the floor because that doesn't affect the normal force between these two. The normal force between the 2 kilogram and the 7 kilogram box is this normal force from the box. So we would use 20 newtons here, and that's going to give us the force of friction for the box is just 12 newtons. So that's the most the tension could be. The minimum force needed to get the 7 kilogram block to move. So the most needed to get it to move would be when they're equal. Obviously more than that, it would start to accelerate. So we want the force applied to be equal to the force of friction from the floor and the force of friction from the box. Well, we just found the force of friction from the box, it's 12. Force of friction from the floor, we would use the coefficient between the floor and the block, which is 0.5. And we would use the normal force of the floor on the block, which was 90 newtons. So that's going to give me 45 newtons, and then those two friction forces together would give me 57 newtons, which is what the applied force would have to be in order to ever overcome both friction forces. Okay. A crate of mass 100 is at rest. The coefficient of static friction between the crate and the floor is 0.4, and the coefficient of kinetic is 0.3. A force F of magnitude 344 is applied to the crate parallel, which is true. So draw a free body diagram. The force of gravity would be 1,000, and that would also be my normal because it's on the horizontal floor. I have an applied force of 344. Now, because it started at rest, in order to get it moved, it has to overcome the static friction force. So static friction would be mu Fn, and that would be 1,000, and I would use the static coefficient, which is 0.4, so that would give me 400 newtons. So if I only pull it at 344, that is not enough to overcome the static friction, so it would not move. So it would not accelerate, nope, because it wouldn't get to the kinetic because it wouldn't start moving. The static friction force, which is a reaction force to F as guaranteed by Newton's third law, will also have to be 343. Well, if it's not moving, my friction force does have to be 344 because it's balanced, it's not moving. But that is not because of Newton's third law. Newton's third law is saying between two objects, the first object on the second equals to the force of the second on the first. That's saying the applied force has to equal the friction. That is not always true, only when it's at rest, so that's not the right reasoning. Right answer for the wrong reason. And this one says it slides across the floor at constant velocity. No, because it is not moving. It has not overcome the static friction, and it will not move. Yes, we agree with that. That is the only true statement. At what time will it be balanced? And we're looking at accelerations. Let's think about if they're balanced, my net force is 0. That means my acceleration is 0. So acceleration is 0 at 2 seconds. That's the only time when it would be balanced. Here, this is a negative acceleration, so that could be like a net force to like the left or down. And then here would be a positive acceleration. That would be a net force in the positive direction. Only time where it's balanced is for this instant where it has 0 acceleration. Using the graph above, what is the net force at 1 second? So F net is equal to ma, mass of 5. Acceleration at 1 second was -2. So that gives me -10 newtons. And the negative just means the net force is in the negative direction, whether that's left or down or etc. A boy is pushing a 50 kilogram crate across a frictionless surface. The velocity is changing with time as shown. What is the magnitude the force applies to the crate? So again, the force is mass times acceleration. We have mass is 50. This is not a graph of the acceleration, it's a graph of the velocity. But we know that velocity over time gives me my acceleration, so you could think of it as like the v equals v naught plus at. You can start at the beginning and go all the way to the end. Time would be 10 seconds there. You're looking for a. The velocity at the beginning was -2, and velocity at the end was 3. You would just add this over. 5 equals a times 10, so a is 0.5. You multiply by that, you get 25 newtons, which is your answer. You also could think through this as, instead of plugging into this equation, just, okay, velocity over time gives me acceleration, that's my slope. So if you go over 1, you go up 0.5, or do like your change in y over change in x, which is essentially what this equation is. Doesn't matter how you like think through this, but the slope would give me my acceleration of a velocity versus time graph. Here, this is a position versus time graph. So this shows constant velocity forward. So if it's moving at constant velocity, it's not zero velocity because it is moving forward. That doesn't make sense. It is not an increasing force because it's just staying at constant velocity. It's not accelerating. The motion is constant positive net force. Actually, no, there's no net force because constant velocity means no acceleration, so F net would be 0. It's balanced forces, no net force. 28, this graph depicts the velocity of a skydiver over time during a free fall. Which of the following statements is true? So we're talking about a velocity versus time graph. So you think he starts with 0 velocity, and then obviously his velocity is getting faster and faster, and then at the end it's staying constant. So I want to say, yeah, it stays constant, stays constant, stays constant until the velocity becomes 0. No, that's not true. It starts 0 and then it definitely goes to a velocity. So now we can cross off E, go back to O and C, because the velocity definitely is changing, so there was net forces at some point. So let's think about the net forces increase until the acceleration is at a maximum and the velocity becomes constant. If the acceleration is at a maximum, then the velocity should definitely be changing very quickly, so that doesn't make sense. The net force decrease until the acceleration reaches 0 and then the velocity is constant. That is true, because when the acceleration is 0, then that's when the velocity stops changing and would stay the same. The net forces increase until the acceleration is 0. You get acceleration 0 when your net force is 0, so that doesn't make sense either. 29. A wooden box is first pulled across a horizontal steel plate. As shown, the box is pulled across the same steel plate, but inclined. How does the friction force compare? So mu is going to be the same for both. So if it's the same for both, and we're looking at mu Fn, we're really looking at like which one has a different Fn. So this one has a greater Fn, this one has a less Fn. And if they have the same mu but a greater Fn, that means this one has a greater friction force and this one has less of a friction force. So then the answer is the inclined case has less friction, C. Last page, thank goodness. I have 3 masses. The coefficient of kinetic friction is mu. What would be the upward acceleration of mass 3? So that tells me that it accelerates this way. And the mass and friction of the cords are small enough to produce a negligible effect. So draw your free body diagram. This would be M1G and then T1. This would be tension 1 and tension 2. This would be M3G and T2. So net force would be M1A equals M1G minus tension. Net force here would be the M3A equals the tension minus the weight because it's accelerating up, not down, and this is T1. Now we want to write our net force equation for this guy. It says that there is a coefficient of friction between M2 and the table. If it's moving this way, then your friction would have to be to the left. So my net force for M2 would be T1 minus T2 and minus the force of friction. Because it's going this way minus force of friction and T2 this way. And we would replace F net with M2A. And we can replace T2 would just be M3A plus M3G equals T2. So we can replace T2 right here with M3A plus M3G. Minus force of friction would be mu, the weight of this one, which is just M2G. And then T1, I would add this over and subtract over. So T1 is M1G minus M1A. So M1G minus M1A. And then now we are trying to solve for, what am I trying to solve for? A? Yeah. So I have an A here, I have an A here, and I have an A here. So we move all the A's to one